unipolar devices. And we know that in bipolar devices or bipolar technologies, the conduction or the flow action of the current is due to both minority carriers and majority carriers. But in MOS technology or in unipolar technology, the conduction is due to only majority carriers. The conduction is due to majority carriers only. Okay. So we know that quite popular devices in bipolar technology that you have come across is they are resistors, diodes, and NPN and PNP junction BJTs. While in unipolar technology, the famous devices which are quite popular are field effect transistors. They are generally known as FETs also. Now, these field effect transistors, FETs, can be either JFETs or they can be either MOSFETs. So, MOSFETs basically come under the category of field effect transistors. Okay. And so unipolar technology is based upon the use of field effect transistors as the active devices in which the controlled current flow is by majority carrier only, unlike bipolar devices in which the flow of current is due to majority carriers as well as minority carriers. So there is a classification in these FETs or in these unipolar devices. We call sometimes it N-channel devices or P-channel devices. By that we mean to say that if the flow of electrons, if the majority carriers are only electrons, then we say that this device is N-channel device. And if the flow of current in these unipolar devices is due to majority carriers only, then we say that the device is p channel. So we can conclude then in n channel devices the flow of carriers between source and drain.
एक्सक्यूज मी सर.
Source and drain, yes.
सर अब थोड़ा ऊंचा बोलेंगे सर. थोड़ा आप धीरे से बोल रहे तो थोड़ी कम आवाज आ रही है.
Okay, okay. Is it fine now?
यस सर.
Okay. So what I was saying that in unipolar devices, in unipolar devices, just a second. So I was saying that in unipolar devices, if the current is due to electron, then these devices are known as n-channel devices. N-channel devices. And if the current is due to holes, then these devices are known
सर
as
स्क्रीन बहुत
p-channel
छोटा आ
devices.
रहा है
Okay,
सर.
I'll
ये
adjust. हाँ हाँ एक मिनट रुको बेटा. Uh, is it fine now?
यस
ठीक
सर.
है?
यस सर.
Okay. So I was saying that in unichan in these unipolar devices, that is field effect transistors, there are two types of devices. One is N channel and P channel. And I said that if the current is due to majority carriers and majority carriers are electrons only, then it is N channel device. And if the current is due to holes, then we say that it is a P channel device. Okay. Now see, we have a classification of electrodes in BJTs, which are as collector, base, and emitter. Okay, we nominate three electrodes of a BJT as collector, base, and emitter. But here, the nomination is like gate, source, and drain. Okay, gate, source, and drain. In field effect transistors, the three terminals are named as gate, source, and drain. So you have G, then you have S, and then you have D. If you can see the last diagram and last but one, you have drain at the top, you have source at the bottom, then on the left hand side you have gate. Okay. So field effect transistors, they are also three terminal devices, just like BJTs. Sometimes there can be fourth terminal as body terminal or substrate terminal, but generally they are three terminal devices, just like BJTs. But the terminals are not named like emitter, base, and collector. Rather, they are named as source, drain, and gate. The third electrode, which is gate, the potential is applied to the third electrode, which is a gate. And the job of this gate is to control the number of free carriers flowing in the channel. Okay. Channel is the space between source and drain. Channel is the space of the semiconductor, or the semiconductor between source and drain. So the job of this gate is to control the flow of carriers in the channel. I'll explain how it will help in controlling that. So this is just an introduction. Hence, source to drain current, because whatever current flows through the channel, remember, channel is the area between drain and source, and whatever current flows through the channel, it is known as source to drain current or drain to source current. Okay. And it is already seen, if you can observe figure 3 after A, B, and figure 4, that is marked in this on this slide, where it is mentioned water analogy for the JFET control mechanism. You can see that the water is coming from source and it is going to drain. You can take an example of drain current like that, that it is coming from source, the current is coming from source and going to drain. What is the job of the gate? Job of the gate will control the flow of this water inside this tap. Similarly, in these devices, the job of the gate, if you apply more potential to the gate, probably it will enhance the current or it will decrease the current. If you release the gate potential, then it can control accordingly. So gate has the same analogy as shown in this figure 4. The figure the picture after figure 4 is JFET picture. We do not have to discuss JFET, but the last one is MOSFET, the last one. Okay, extreme right pe jo bottom mein hai, that is our MOSFET. Okay. And you have to remember that, so this is MOSFET, this one is our MOSFET. And what is the full form of MOSFET? MOSFET is metal, O is oxide, S is semiconductor, then FET is field effect transistor. Okay. And we know that electrons in general have higher mobility than holes. Therefore, N-channel MOSFETs or N-channel FET or N-channel unipolar devices, they are faster than P-channel devices, roughly by a factor of 2.5. Roughly by a factor of 2.5. So what is the job of the gate now? The gate control of the FET may be, how can we control this gate terminal in these field effect transistors? By applying certain potential, by applying certain voltage on it. Okay. If you observe these three diagrams, in the first diagram, we can see that gate is floating. In diagram number 1, the gate is floating. And please remember that the gate is connected to P side of semiconductor. Generally, this is the JFET diagram. This is junction field effect transistor. Okay. You can observe from this diagram, you have somewhere drain, then you have source, which is made up of N-type semiconductor. There is no other P-type of semiconductor between source and drain. But sideways, you have P-type diffusion there. You have P-type semiconductor part in this device. So wherever P is in contact with N, it will form a PN junction. Okay, so we have a PN junction on right hand side, PN junction, which is gray. Okay, then you have another PN junction on left hand side. So there are two PN junctions, and if we apply a P type, a positive to P side and a negative to N side, this PN junction will be forward biased, and the depletion region, which is marked by this gray region. So this is depletion region that I am highlighting on the slide. This will decrease. This depletion region will decrease. But if we reverse bias this PN junction, so we have two PN junctions here in this device. One is here and another is somewhere here. So if we forward bias this PN junction, then depletion region will decrease. But if we reverse bias this PN junction, then this depletion region will increase. And the channel width, what is the channel? Channel is space. Channel is basically space between source, sorry, drain at the top and source at the bottom. So this entire area between source and drain, it is known as channel. And this is the width of channel. This is the width of channel. Width of channel. This is length of channel. Okay. The first one is length of channel. If we increase the reverse bias on these PN junctions, we can understand, we can observe that width of depletion region will decrease. Oh, sorry, it will increase. Width of depletion region will increase. And if width of depletion region increases, then the width of the channel will decrease. Eventually, the current flowing from source to drain, it will also decrease. The current flowing from source to drain, it will decrease. And if we increase reverse bias too much, if we increase reverse bias too much, that is on P side, some more negative voltage is applied on P side, some more negative is applied, and on drain side, that is N side or source side, some more positive is applied. And if we have a very high reverse bias, then there will be a point when the depletion region will be so large that it will block the channel, and this point is known as pinch off point of the channel.
सर
Go
ये
ahead.
समझ ही नहीं आया सर। सर आप ये रिपीट करें।
कौन सी चीज?
सर यही जो जब ये ना ये विड्थ वगैरह ये इसका मॉसफेट का।
ये जेफेट है फर्स्ट ऑफ ऑल।
सॉरी।
हाँ, थोड़ा सा दिमाग रखो एंड ट्राई टू फोकस व्हाट आई एम सेइंग, ठीक है? तो इट इज बेस्ड ऑन द डायोड थ्योरी। व्हाट आई एम सेइंग हियर इज दैट वी हैव टू डिफरेंट पीएन जंक्शंस। हमारे पास दो पीएन जंक्शंस हैं एक जेफेट में, एक है राइट साइड से, एक है लेफ्ट साइड से। और उस पीएन जंक्शन की, तो दिस इज अ पीएन जंक्शन हियर, आई विल ड्रॉ इट हियर। सो दिस इज JFET, ये है P एंड यू है N टाइप सबस्ट्रेट। अब P जहाँ N से करेगा कांटेक्ट वो एक जंक्शन बनाएगा, तो PN जंक्शन में डिप्लीशन रीजन होता है। Normally if we will go for a forward biasing, then this depletion region will be small. But if you will go for reverse bias, this depletion region will be quite large. So ये है शक्ल depletion region की when you go for reverse biasing. This is the width of depletion region when you go for forward bias. So if we change the reverse bias on these depletion regions, what will we attain? We are basically controlling the width of the channel. Width of the channel. तो channel में जो width है, हम reverse bias से उसको control कर सकते हैं in these devices. How we are going to control it? By changing the width of the depletion regions. Depletion region is always formed when you have a p-type semiconductor in contact with n-type semiconductor. If you remember p-n junction, you have p and n in a diode. Then the intersection between p and n, it forms a depletion region. It forms a depletion region. So this is depletion region. तो यहाँ पे भी पी एन है, यहाँ तो एक you have this is n type substrate and this is p type well here, p type. तो जहाँ p और n आपस में टच करेंगे, it will form a depletion region. अब इस depletion region की width हम change कर सकते हैं, that is quite easy for us by changing the biasing. अगर हम forward bias करेंगे तो depletion region जो है it will be small. If we will reverse bias it, depletion region will be quite large. And if we reverse bias it too much, that gray area, this depletion region will be too large that they will touch from each side. लेफ्ट हैंड साइड से राइट हैंड साइड के साथ टच करेगा, तो चैनल में जो गैप है जहां से इलेक्ट्रॉन मूव कर रहे हैं फ्रॉम सोर्स टू ड्रेन, वो बिल्कुल बंद हो जाएगी, वो रास्ता ही बंद हो जाएगा। हमाद, इज इट ओके नाउ?
यस
समझ
सर।
में आया? समझ में आया बेटा ये?
यस सर।
हाँ ठीक है। व्हाट अबाउट रेस्ट? रोल नंबर 27 है यहाँ पे।
जी सर।
आपको समझ में आया बेटा?
यस सर।
कोई सवाल तो नहीं है?
नो सर।
So we can conclude that VGS is basically VGS is basically gate to source voltage. सोर्स वोल्टेज यानी गेट पे अगर ऐसे करेंगे, एक टर्मिनल गेट के साथ होगा, एक टर्मिनल सोर्स के साथ होगा, दैट इज नोन एज VGS. तो अगर VGS पॉजिटिव होगा यहाँ पे, if VGS is zero, then depletion region will be small, nominal, and there will be channel, there will be some channel. लेकिन अगर डिप्लीशन रीजन पॉजिटिव होगा, जैसे मैंने इस वक्त दिखाया है, जैसे इसमें इस वक्त मैंने दिखाया है डिप्लीशन रीजन, sorry, biasing VGS, then depletion region will be small. Why? Because PN junction is forward bias. लेकिन अगर depletion region as sorry, if VGS will be in this way, reverse, this is VGS, that means positive terminal is connected to N side and negative terminal is connected to P side. Then the bias on the PN junction will be reverse bias. Then PN junction will be reverse bias, depletion region की width ज्यादा होगी. और जब डिप्लीशन रीजन की विड्थ ज्यादा होगी, उस हिसाब से चैनल को आप छोटा, तंग या और बड़ा कर सकते हैं. यू कैन मेक इट स्मॉल, नैरो, एंड you can change the width of this channel. And if you are able to change the width of the channel, it means you are basically trying to control the flow of electrons. You are trying to control flow of these electrons in this device. And please note it down, where is the flow of electrons in these MOSFETs? It is always from source to drain. Okay, it is always from source to drain. So electron always moves from source, goes to drain. So generally there is a potential between drain and source connected like this, which is known as VDD, or it is also known as VDS. So when you have a positive terminal connected at drain and a negative terminal at source, so अगर यहाँ पे कोई electron होगा in this channel, it will be repelled and positive will attract it. So it will be pulled towards drain. That is why I am saying that current in these devices will always move from source to drain. अब कितनी करंट फ्लो होगी वो डिपेंड करेगा व्हाट इज द विड्थ ऑफ दिस चैनल, इस चैनल की विड्थ कितनी है. आप उसको कम ज्यादा कर सकते हैं. यू कैन इंक्रीज द रिवर्स बायस, you can increase the reverse bias, and then you can construct it also. ठीक है, you can in other words you can control the entire current flowing through source to drain. Generally the current that flows from source to drain, it is known as drain current, ID. It is known as drain current. It is known as ID, drain current. Anyway, so this is how these devices work. It was about JFET, but there are certain features which are present in these unipolar devices or MOSes, which are quite advantageous than bipolar devices. First of all, bipolar devices have also significant feature as compared to MOSFETs. Bipolar devices are faster than MOSFETs. They are faster, and but they usually take more power dissipation. They can consume a lot of power. So BJTs are faster, but they can consume more power, and they have a higher transconductance also. Transconductance parameter will be determined in incoming lectures. So they have higher transconductance also, and which is a parameter basically used in amplification. So if you have a higher transconductance in a device, it means that you can have a better amplification, signal amplification. So BJTs are better amplifiers as compared to MOSFETs or FETs because of presence of higher transconductance in them. And the third point is that BJTs are quite easy to fabricate. There are fewer fabrication steps required compared with this high performance MOSFET. In MOSFETs, you require many steps, and a very professional and a complicated setup is required to manufacture them. But in BJTs, the fabrication steps are fewer and they are quite simpler as compared to MOS and CMOS fabrication techniques. Okay, so this is only one point, it is not 2 points. So, but inherently MOS also have some advantages. They also have a upper hand as compared to bipolar devices. So what is the upper hand in them? What is the advantage? What are advantages in them? they generally have higher impedance levels, input impedance levels. And you know that amplifiers, it is a preferable parameter in amplifiers to have high input impedance. High input impedance. I have already explained in the class why. Okay. So generally they have much higher input impedance levels than bipolar, thus reducing on-chip dissipation. So you have already heard it that BJTs have more power dissipation, but uh, here in MOS you have less power dissipation. Why? Because their input impedance is very high. Input impedance is very high. Okay. So the second important advantage here is that device performance, that is how much efficient your device MOSFET is, it is strongly dependent upon the device geometry. This is a very important parameter, that if you change the geometry of the MOSFET, its performance will also change. Maybe it will not be able to amplify that much, or it will amplify in a better way. तो इसकी इसकी जो बनावट है, खदोखाल है, जो इसकी लेंथ है, इसकी विड्थ है, उस पे इसकी परफॉर्मेंस काफ़ी ज़्यादा डिपेंडेंट है. So this makes, this gives us an advantage that we can tailor it down. We can tailor it down. We can cut the length and increase the width, or decrease the width or increase the length as per our demand, so that we can make it, compatible with our own performance, desired performance. So this parameter, that device performance is strongly dependent on device geometry. It makes us readily possible to tailor this device performance during the chip layout stage. Chip layout stage is manufacturing stage. Okay. So when we manufacture, we can tailor these MOSFETs. We can cut its geometry or adjust its geometry in such a way so that it fits our application. जिसमें जो application हमें करनी है. For example, we want some kind of gain in these devices. 100 is the gain that we want. So apart from this, apart from this metallurgical process कि इसमें इंजेक्शन कितनी होनी चाहिए, डोपिंग कितनी होनी चाहिए, हम इसको साइजिंग ऐसे करते हैं so that we get an appropriate gain. तो वो भी एक एडवांटेज इसमें है, which is a facility completely absent in bipolar technology. वो bipolar technology में ऐसा कुछ नहीं होता है. uh, uh, okay, all right. So this is an hierarchy which will tell you field effect transistors, which are controlled by applying certain potential at gate. The devices जिनमें gate terminal होता है present, they are broadly classified into two different categories. One is known as junction field effect transistor, another is known as IGFET. IGFET is basically MOSFET. So we are trying to understand the structure of MOSFET. So we will not discuss IGFET, but we'll discuss MOSFET. MOSFET is further classified into two different categories. One is known as metal oxide semiconductor field effect transistor, which is actually made up of metal gate. Usme gate terminal, which is here, the gate terminal is made up of metal actually. The another part of it, the another classification is polysilicon gate devices. Here, the gate is made up of polysilicon. Polysilicon is a polymer, conducting polymer, okay, which is quite cheaper, and it has certain advantages also. Currently, in this, modern MOSFETs are mostly made up of polysilicon. Modern MOSFETs are mostly made up of polysilicon. There, the gate is made up of polysilicon, but in MOSFETs, actually, gate is made up of metal. But in today's world, we use this MOSFET term for polysilicon based devices. तो ये जो MOSFET का नाम है, ये उन डिवाइसेस के लिए भी यूज होता है जिनका गेट मेटल का बना होगा या चाहे उनका पॉलीसिलिकॉन का बना होगा. इट्स अ जनरल टर्म नाउ. इट हैज बिकम अ पॉपुलर टर्म नाउ इन बोथ डिवाइसेस. सो आजकल के ज़माने में जब हम MOSFET कहते हैं, ये भी हो सकता है दैट इट्स गेट इज मेड अप ऑफ पॉलीसिलिकॉन. But generally, actually, in MOSFETs, the gate should be made up of metal terminal, and source and drain are then made up of semiconductors. But in polysilicon based devices, gate is made up of polysilicon, and source and drain are made up of semiconductors. रोल नंबर 38 आपको ये समझ में आ रहा है बेटा, ये मैं जो कह रहा हूँ?
यस सर.
ओके, ऑल राइट, व्हाट अबाउट 51? उरुजा को समझ में आ रहा है?
Yes, sir.
अरबा को समझ में आ रहा है?
Yes, sir. Yes, sir.
Okay. Now, see, these MOSFETs or polysilicon-based gate devices, or in general MOSFETs, they are further classified into depletion mode and enhancement mode type devices. In depletion mode, channel is initially present. Okay, so when channel is present, it means charge carriers are inside the channel. It is generally conducting. Normally, it is conducting. In order to turn it off, आपको गेट पे कुछ पोटेंशियल करना है अप्लाई, तब जाके ये ऑफ हो जाएगा. So channel is initially present and it can conduct in normal state. And if you want to turn it off, then you have to apply certain gate potential. In enhancement mode devices, channel is initially absent. And if you want to make it conducting, you have to first apply certain gate potential, create the channel, then it will conduct. I will explain this in coming slides. So depletion and enhancement mode would mean that channel is initially present for conduction, and enhancement mode may we need to enhance the channel for the conduction. Okay. So depletion and enhancement mode, both this is a classification present in polysilicon and MOSFET as well. दोनों में ऐसी classification है. They are further divided into two different classes. One is N channel and P channel device. मैंने पहले भी कहा है. In N channel device, conduction is due to electrons. ठीक है? And in P channel device, conduction is due to holes. It is due to holes. Conduction is due to holes. Okay. So we'll discuss these N channel and P channel devices in coming slides also. Now see, these are various symbols for these N channel and P channel devices. First of all, I said that FETs have three terminals. Field effect transistors have three terminals. Lekin we can have one extra terminal which is known as body terminal or substrate terminal. I will explain why this terminal is there and what is substrate terminal. So you can see sometimes four terminals. तो यहाँ कभी तीन भी हो सकते हैं, कभी दो भी हो सकते हैं. तो अगर आप नीचे देखेंगे right bottom पे you have a PMOS. Okay, so you have three terminals only: source, drain, and then you have gate. If the arrow is pointing inwards on the source, then it means it is PMOS. अगर ये source terminal पे arrow रखा गया है and it is pointing inwards, it means it is PMOS. So you can have three terminals or you can have sometimes four terminals also. तो ये बस कभी कभार बॉडी टर्मिनल या जो सबस्ट्रेट टर्मिनल है उसको कभी नहीं दिखाया जाता है या कभी दिखाया भी जाता है, बिकॉज द ऑपरेशन इस लेवल पे जो ऑपरेशन हम डिफाइन करते हैं उसके लिए तीन ही टर्मिनल्स इंपॉर्टेंट हैं, फोर्थ इज नॉट इंपॉर्टेंट एट दिस लेवल. ओके, so please note it down. When the arrow is shown on the source, when the arrow is shown on the source and it is pointing inwards, then it is PMOS. But if it is arrow is marked on body, if it is marked on body, if the arrow is marked on body, please note it down. Then it should be outwards in PMOS. तो यहाँ अगर बॉडी पे है तो ये आउटवर्ड्स है, अगर सोर्स में है तो इनवर्ड्स है. तो ऐसी डिवाइसेस को हम कहते हैं, दिस इज द सिंबल फॉर PMOS. Similarly, in NMOS, if it is marked on source, PMOS में ये अंदर था, it was going inside. So in NMOS, it will go outside. Okay, it will go outside. And if it is marked on body terminal, then it should go inside. It should go inside. तो वो उसका उल्टा है. So these are the symbols of PMOS and NMOS transistors. कभी कभार हमारे पास कुछ किताबों में ऐसे भी होता है. If it is shown like this is source, drain, and this is gate, then it is NMOS. NMOS means N channel. N channel MOSFET. But if you have something like this, you have a bubble at the gate, drain, source, and gate. If you have a bubble on the gate, then it is P channel. So PMOS वो मैंने यहाँ पे दिखाया है. So you have a bubble somewhere here You have a bubble here, so it is p channel MOS, but you have no bubble here. Okay, no bubble on the gate, then it is NMOS. This is PMOS and NMOS symbols. अब क्योंकि ये डिवाइसेस एनहेंसमेंट भी होती हैं एंड डिप्लीशन टाइप भी होती हैं, तो एनहेंसमेंट में इफ यू हैव अ डिप्लीशन टाइप मॉसफेट, देन द लाइन बिटवीन ड्रेन एंड सोर्स विल बी कंटिन्यूअस. इसमें कहीं परफोरेशंस नहीं होंगी, इसमें डिसकंटिन्यूटीज नहीं होंगी. तो जिनमें सोर्स और ड्रेन तक जो लाइन है, if it is continuous, it means they are depletion type symbols. But if you have certain discontinuities like this, ठीक है, तो गेट के नीचे जस्ट बिलो द गेट अगर इसमें थोड़ी परफोरेशंस हैं, थोड़ी सी कुछ डिसकंटिन्यूटीज हैं, इट मींस it's a symbol for enhancement type device. So these are various symbols for this MOSFET that we use. Now this is the structure of a MOSFET. ठीक है, MOSFET का structure ऐसे है. Please remember that on the right hand side you have a large mass of semiconductor like this. You have a large mass of semiconductor. It is known as substrate or it is known as body also. ठीक है, जो ये पूरा blue है, this is substrate. It is the structure of MOSFET. ये JFET का नहीं है. It is the structure of MOSFET. So this is all substrate or body of the device. Body of the device. The job of the substrate or the body is to provide the physical support to rest of the structure. जो इसमें दूसरा structure होता है. Okay, rest of the structure. What is the rest of the structure? So this is body. If you will see that, if you observe it carefully, in the body there are two different wells. They are of opposite type. अगर body P type substrate है, P type semiconductor है, then the wells, it is important that wells should be of opposite type. You cannot have P type wells here. तो then you have N type well. तो एक कुआं यहाँ है, एक वेल यहाँ है और एक वेल राइट हैंड साइड से, एक वेल लेफ्ट हैंड साइड से है. And it is N type. It is also marked as N plus. N plus would mean N but highly doped. Plus means highly doped. Highly doped N type semiconductor. It means highly doped semiconductor. 46 को ये समझ में आ रहा है बेटा? कोई सवाल तो नहीं है?
वो सर आ रहा है समझ में.
फहीम को समझ में आ रहा है रोल नंबर 2 को? रोल नंबर 2. What about 4?
Yes sir, yes sir.
Okay. What about 13? 13 को समझ में आ रहा है?
Yes, sir.
Roll number 4, please turn off your mic.
Okay, sir.
What about Murtaza? Murtaza को समझ में आ रहा है?
जी सर.
उबैर को 49.
जी सर.
ओके, तो मॉसफेट में एक सबस्ट्रेट होता है, ओके, और इसमें दो वेल्स होते हैं एन टाइप के. एन प्लस का मतलब है हाईली डोप्ड एन, हाईली डोप्ड एन. ठीक है, एन टाइप सेमीकंडक्टर. नाउ सी, any one of them, one can be called as source, another is called as drain. तो इसमें लेफ्ट हैंड साइड से ड्रेन है और राइट हैंड साइड से, सॉरी, लेफ्ट हैंड साइड से सोर्स है एंड राइट हैंड साइड से ड्रेन है. But please remember that these n wells are identical wells. You can even call right hand side as source and left hand side as drain. इसमें कोई फर्क नहीं होती है. एक टर्मिनल इन दोनों में से सोर्स माना जाता है, एक ड्रेन. तो यहाँ मार्क किया गया है लेफ्ट से सोर्स और राइट से ड्रेन. ये जनरल कन्वेंशन है, लेफ्ट साइड से सोर्स रखते हैं, राइट साइड से ड्रेन रखते हैं. लेकिन क्योंकि इनमें मेटलर्जिकली कोई फंक्शन, देयर इज नो डिफरेंस मेटलर्जिकली, दे आर नॉट डिफरेंट, they are identical. You can even mark right side source and left side as drain. It is quite acceptable. Okay, now apart from these two wells, there is a thin layer which is before that, the area between source and drain, or the area between source and drain, this is the area. ठीक है, ये जो ये area है, the area between source and drain it is known as channel of the device. It is channel, ठीक है? And L is the length of this channel. L is the length of this channel. So the area between source and drain is channel. Area between source and drain is channel. So this is the channel. This is somewhere channel. ठीक है? तो ये है असल में channel. Channel हमेशा source और drain के बीच में होती है. Just above the channel, you will see white color, hatched lines. एक layer होगी white color की. So this layer is the green one that I have marked here. It is a thin oxide silicon dioxide layer. ये छोटी सी layer जो है बहुत ही पतली होती हैं. It is known as silicon dioxide. So there is a deposition of silicon dioxide layer, okay, whose thickness is equal to Tox. So this silicon dioxide is always just above the channel. Above the silicon dioxide layer, there is a black layer, which is metal layer, and it is known as gate. So please note it down that gate terminal is always above the channel, separated by silicon dioxide. तो जो ये isometric view है on the left hand side, you can see that this is drain and this is source terminal. अब source and drain पे भी black areas हैं. ये black areas metal contacts हैं ताकि ये source के साथ या drain के साथ electrically contact हो जाएं और बाहर इसके connections आ जाएं. So you can see that in the left hand side isometric view or 3D view of this MOSFET, this is the length of the channel. Okay, L is the length of the channel. Width of the channel is the width of the device. Width of channel is W. And it is width of device. Okay, width of channel is W and it is width of device. And you can also see that you have a small white layer of silicon dioxide. Okay, silicon dioxide होता है इसमें. And you can sometimes have body terminal also. उस पे भी metal होगा थोड़ा सा ताकि connection बाहर आ जाए, so that the connection will be taken out and it will be connected to rest of the circuit. Okay. Now see, what is the job of the substrate, the body part? The transistor is fabricated on a p-type substrate, which is a single crystal silicon wafer that provides physical support. तो जो body का job होता है, it is there to provide physical support for the device. पूरी device के लिए ये physical support देता है, एक बुनियाद देता है, okay, एक foundation बनता है उसके लिए. And for the entire circuit in case of integrated circuit, जब आप IC बनाते हो उसमें substrate ही सारे जो पुर्जे ऊपर वगैरह से जितने भी components लगते हैं और areas जो manufacture होते हैं तो वो उनमें उसको support दे देता है. Now see, two heavily doped N-type regions, that is this one and this one, indicated in the figure as N1 source and N plus source and N plus drain regions are created in the substrate. ये substrate में ही होते हैं. A thin layer of silicon dioxide of thickness Tox, typically the thickness is 1 to 10 nanometer. Please note it down. The thickness of silicon dioxide is typically 1 to 10 nanometer. So it is very thin, which is an excellent electrical insulator. And this silicon dioxide is electrical insulator also. So in these MOSFETs, please note it down, gate terminal is electrically isolated from rest of the device. तो gate को electrical connection नहीं होता है body के साथ या channel के साथ या source drain के साथ. ये हमेशा electrically isolated होता है. That is why they have input impedance very high. इनकी जो input impedance है इसी वजह से ज़्यादा होती है. So which is an excellent electrical insulator, is grown on the surface of the substrate, covering the area between source and drain regions. Okay. So this is, I'm discussing the construction of this MOSFET. Metal is deposited on the top of the oxide layer to form the gate electrode. So this metal on the top of the silicon dioxide, this entire black region is nothing but it is the gate terminal. Okay. Metal contacts are also made to source region, the drain region, and the substrate, also known as body, Thus, four terminals are brought out: the gate terminal, the source terminal, and the drain terminal, and the substrate or the body terminal from this MOSFET. Okay. It must be noted that the name of the device, metal oxide semiconductor field effect transistor, is derived from its physical structure. असल में जो इसका physical structure है, कहीं कहीं semiconductors हैं, कहीं कहीं semiconductors हैं, कहीं कहीं metal हैं, और कहीं कहीं oxide है, कहीं कहीं oxide है. इसीलिए इसको कहा जाता है metal oxide semiconductor, and it works on field effect transistor. Field effect transistor. ठीक है. So that is how the MOSFET is manufactured. इसकी बनावट ऐसी ही होती है. This is the construction of the MOSFET. Okay. Now, as far as working is concerned, we define its working into two different, in three different modes. How it works. MOSFET. Roll number 12 is here. 12.
यस सर.
हाँ, समझ में आया बेटा ये कंस्ट्रक्शन?
यस सर. यस.
हाँ, बनावट
Yes, sir.
इसकी समझ में आई. किसी को कोई सवाल तो नहीं है कंस्ट्रक्शन में? यू कैन आस्क मी इफ यू हैव एनी क्वेश्चन अबाउट दिस. MOSFETs are also known as IG FETs, insulated gate FETs, because the gate is insulated, because this is insulation. Silicon dioxide is nothing but it is insulation. ये electrically isolated होता है, तो इट्स एन इंसुलेशन. तो इसको कहा जाता है इंसुलेटेड गेट फील्ड इफेक्ट ट्रांजिस्टर भी कहा जाता है इनको, आईजी फेट्स. तो मॉसफेट्स का दूसरा नाम आईजी फेट भी है. किसी को कोई सवाल तो नहीं है? रोजा को कोई सवाल है? रोजा इज नॉट.
No, sir.
व्हाट अबाउट महराजदीन को कोई सवाल तो नहीं है?
नो सर.
76.
No, sir.
Okay. ठीक है. So now see, in this diagram, I am actually trying to highlight only this much area. ठीक है, मैं खाली इस एरिया को हाईलाइट कर रहा हूँ और उसको यहाँ प्रोजेक्ट कर रहा हूँ. तो ये जो ये आप देख रहे हैं, this is nothing but channel area only. Okay, channel area only. So this is channel area only. असल में है ये ऐसे. ठीक है, तो ये असल में ये एरिया है. Now see, working of MOSFET. How does it work? Its operation. There are generally three modes of operation in MOSFETs. Okay. First of all, first mode is known as accumulation mode. Accumulation mode. Okay. Now see, if you have a MOSFET like this is your source, this is your drain, and this is, for example, your gate. So whatever voltage is applied between gate and source, it is known as VGS. ठीक है, VGS. It is known as VGS. VGS is the voltage between gate and source. Now see, accumulation mode for an N-channel MOSFET, you should note it down. अगर substrate P-type है, अगर substrate P-type है, P-type substrate, then we call it is an N-channel MOSFET, N-channel device. अगर substrate N-type है, तो डिवाइस को कहा जाता है P टाइप. ठीक है, मैं वो बताऊंगा क्यों कहा जाता है उल्टा इसका. So this is an N channel device. This is an N channel device. Why? Because substrate is of P type. For an N channel MOSFET, if VGS is much lesser than VT, VT is the threshold voltage. VT is the threshold voltage. Likewise, you were using knee voltage VK in the diodes. आप कहते थे knee voltage के बाद diode starts conducting. And before knee voltage, diode is off. Similarly, यहाँ एक voltage होती है, उसको कहा जाता है threshold voltage. After threshold voltage, MOSFET turns on, channel is created, and before threshold voltage, channel is not created. Okay, so MOSFET is off. So for channel, it is necessary that input voltage, which is VGS, should be greater than VT. Okay. So this is VGS, and this is, for example, diode current. Device current, drain current, ID. तो अगर इनपुट वोल्टेज VT से ज़्यादा होगी तो डिवाइस ऑन होती है, चैनल इज क्रिएटेड, and if it is less than, then it is not on. Now, if VGS is less than VT threshold voltage, it can be this much, यानी 0 to VT, या ये नेगेटिव हो सकती है, ठीक है, या तो ये बिल्कुल लेस देन 0 होगी. In both these cases, VGS is less than VT. So I said that either if VGS is less than VT, either it can be this much from 0 to VT, or it will be less than 0, it means negative. तो दोनों केसेस में VGS जो है वो है आपका, it is less than VT. अब देखिए, if VGS is less than 0 का मतलब है ये वाला एरिया, ठीक है, लेस देन 0 का मतलब है ये वाला एरिया, तब तो चैनल होगी ही नहीं, तब तो डिवाइस ऑन होगा ही नहीं. लेकिन एक चीज समझना है, इफ VGS is less than 0, it means VGS is negative. VGS is negative because this is a negative region on VI characteristics. It means that you are basically applying a negative voltage on the gate. तो जब VGS नेगेटिव होगा, VGS लेस देन 0 होगा, तो नेगेटिव वोल्टेज गेट पे आएगा, अप्लाई होगा, ठीक है. तो नेगेटिव चार्ज विल बी अप्लाइड ऑन द गेट. सो दिस इज गेट, रेड कलर इज गेट. इट इज बेसिकली पॉलीसिलिकॉन, लेकिन आपके केस में पॉलीसिलिकॉन नहीं होगा, दिस इज मेटल, बिकॉज वी आर डिस्कसिंग मेटल ऑक्साइड सेमीकंडक्टर फील्ड इफेक्ट ट्रांजिस्टर. सो दिस इज मेटल, रेड कलर का एरिया इसमें मेटल है. जो ये ग्रे और दिस ब्राउन एरिया, इट इज इंसुलेटर, it is silicon dioxide insulator, and this part, the blue part, is substrate. तो when negative voltage is applied on gate, तो सारा negative charge metal पे ही होगा, because if you have for example a metal और आप उसको ऐसे करोगे कनेक्ट किसी बैटरी के साथ, तो यहाँ जितना भी पॉजिटिव चार्ज है वो आ जाएगा मेटल पे ही, ठीक है. अगर आप इसको नेगेटिव करोगे अप्लाई, तो नेगेटिव चार्ज मेटल पे डिपॉजिट होगा. So if VGS is less than 0, negative charge will be accumulated on the metal, and this negative charge will attract holes from the substrate. It will not cross and move into the substrate. Why? Because there is an insulator in between. इसमें इसके बीच में substrate और metal के बीच में insulator है. ये क्रॉस तो नहीं करेगा, लेकिन इसका इलेक्ट्रिक फील्ड जो है वो सबस्ट्रेट में होल्स उठाएगा. व्हाई? बिकॉज इन सबस्ट्रेट you have p type substrate, and you have many holes there. You have majority carriers or holes, positive charges. उन सारे होल्स को वो खींचेगा, and it will accumulate them just below the insulator. रोल नंबर 12, ये समझ में आया बेटा आपको?
जी सर.
27 आपको समझ में आया बेटा?
जी सर.
78 को समझ में आया?
Yes, sir.
Okay. Since it will accumulate too much positive charge of P substrate under the gate area, then it is known as accumulation mode. तभी जाके इसको accumulation mode कहा जाता है, ठीक है. अब दूसरा केस होगा, अभी तो था VGS was less than 0. Now another case could be VGS is less than VT, but it is greater than 0. That means this much. थोड़ा सा पॉजिटिव है, लेकिन VT से फिर भी कम है इस रीजन में, यानी इस रीजन में इतना होगा VGS. तब भी डिवाइस ऑफ होगी, तब भी चैनल नहीं बनेगी, because device will not still conduct, because in order to conduct you have to cross VT threshold voltage. But let us see what will happen in the second case. In depletion mode, your input is here. This is, for example, VT. This is ID. This is VGS. So you are in this range. You have not crossed the threshold voltage, but you have still positive voltage. It is greater than 0. Okay? In depletion mode, our VGS is greater than 0, but it is less than threshold voltage. So sum of the positive charge in this case now, what will be the charge that will be deposited on the metal? Definitely positive charge, क्योंकि ये एक positive area है, यहाँ positive है VGS. Weaker positive charge ही सही. It is less than VT. It is very weak. Weaker positive charge ही सही, लेकिन होगा तो positive charge ही metal पे deposit, और बीच में है insulator. अब इस पॉजिटिव चार्ज से जो पी सबस्ट्रेट में बहुत सारे होल्स थे, they will be repelled down, they will be repelled down, okay, they'll be pushed downwards, they'll be pushed down, they will not be attracted and accumulated just under the gate. In fact, they will be repelled down away from the gate, and because of this there will be some depletion region, smaller depletion region will be created. एक छोटा सा depletion region बन जाएगा, ठीक है, just below the gate, just below the gate, a smaller depletion region will be created. That is why it is known as depletion mode. Depletion mode. रिहा, आपको ये समझ में आया?
Yes.
डिप्लीशन रीजन समझ में आया बेटा कैसे बनेगा?
Yes, sir.
तवहीदा को?
जी सर।
Okay. So that is why it is known as depletion region or depletion mode of MOSFET. The third one is interesting one, inversion mode. Now see, here the input voltage VGS, and this is ID for example, you have somewhere here threshold voltage. अब न तो आप इस रेंज में हैं ना आप इस रेंज में हैं. Here VGS is greater than VT. VGS is greater than VT. So you are basically in this range. Okay. So you are in this range. Here you have a lot of positive charge on the gate. So on the gate you are depositing lot of positive charge. What is gate made up of? Metal. तो अब गेट में बहुत ज्यादा पॉजिटिव चार्ज है. तो अपार्ट फ्रॉम क्रिएटिंग ए डिप्लीशन रीजन, पी साइड में जितने होल्स थे वो तो एक एक पहले तो वो स्ट्रांगली रिपेल हो जाएंगे डाउन, ठीक है. फिर अगर कहीं इक्का दुक्का इलेक्ट्रॉन हुआ भी, इफ देयर इज समवेयर इन बिकॉज इन पी टाइप सबस्ट्रेट मेजॉरिटी आर होल्स बट माइनॉरिटी आर इलेक्ट्रॉन्स, तो कहीं कहीं अगर माइनॉरिटी कैरियर्स भी हैं उनको अट्रैक्ट किया जाएगा. दे विल बी अट्रैक्टेड just below the gate towards the insulator, towards silicon dioxide. So it is as if we are basically creating an inversion region just below the gate. तो inversion region यानी inversion region का मतलब है ये था तो पी टाइप सबस्ट्रेट, लेकिन इसमें आपने पी टाइप होल्स को इतना रिपेल किया, इतना स्ट्रॉन्ग पॉजिटिव इलेक्ट्रिक फील्ड दिया ऊपर गेट पे कि इसने माइनॉरिटी कैरियर्स को भी खींचा, यानी माइनॉरिटी कैरियर्स अब जमा हो गए. पी टाइप में होते तो है होल्स, होते तो है पॉजिटिव चार्ज मेजॉरिटी, लेकिन इसने उनको भगा दिया एंड इट हैज कलेक्टेड ऑल द नेगेटिव चार्ज जस्ट बिलो द गेट. सो यू हैव अ लेयर व्हिच इज ऑफ अपोजिट चार्ज नाउ, इन्वर्टेड चार्ज. होना तो चाहिए था पॉजिटिव चार्ज, होल्स होने चाहिए थे और इनफैक्ट होल्स ही कंडक्ट करने चाहिए थे, लेकिन नहीं. अब इसने क्या किया, it has so much high electric field that it has collected all the electrons just below the gate and started accumulating them. So an inversion region is created just below the gate. That is why this is a strong inversion region. It is also known as inversion mode of this MOSFET. तो इसके बाद इन्वर्शन मोड, अब देखिए यहाँ ये चैनल में होगा, ये नेगेटिव चार्ज कहाँ होगा, चैनल में नीचे at the bottom. I am marking it. Now when this inversion happens in MOSFET, then we say that channel is created. तब हम कहते हैं चैनल बनी. अब देखिए पॉजिटिव पी टाइप सबस्ट्रेट में होल्स ज्यादा थे, so there were holes, पॉजिटिव चार्ज होल्स थे. उन होल्स को आपने नीचे पुश डाउन किया और माइनॉरिटी कैरियर्स को चैनल में धकेला, और फिर आपने कहा कि ये जो माइनॉरिटी कैरियर्स हैं यही है मेरी चैनल है. अब अगर आप यहाँ ड्रेन पे पॉजिटिव वोल्टेज अप्लाई करेंगे, एक बैटरी कनेक्ट करेंगे और यहाँ नेगेटिव बैटरी करेंगे अप्लाई लाइक दिस, so the voltage between drain and source, it is known as VDS or VDD. अब अगर आप VDS अप्लाई करोगे, ये पॉजिटिव चार्ज इन इलेक्ट्रॉन्स को जो चैनल में है इनको अट्रैक्ट करेगा, ये नेगेटिव चार्ज जो चैनल में आपको इलेक्ट्रॉन्स है उनको रिपेल करेगा. सो a current will flow in this direction. A current will flow in this direction through the channel. तो जब चैनल बनी तब जाके ड्रेन करंट फ्लो हुई. This is known as drain current. The current that will flow from source to drain through the channel, it is known as drain current. Please remember that drain current तब फ्लो हुई जब चैनल बनी, उससे पहले नहीं फ्लो होती है. And this current is because of electrons in P substrate. That is why it is known as N-channel MOSFET, N-channel device. That is why it is known as N-channel device. Roll number 27 बेटा, कोई सवाल तो नहीं है?
No, sir.
किसी बच्चे को कोई सवाल तो नहीं है मॉसफेट पे? ठीक है, ओके. सो आई डोंट थिंक दैट आई हैव टू एक्सप्लेन इट नाउ. सिमिलरली हियर, ये जो यहाँ डायग्राम दिखाई गई है, इट इज शोइंग दैट a पॉजिटिव VGS इज अप्लाइड. गेट पे एक पॉजिटिव VGS अप्लाई हो रहा है, means too much positive charge on gate, and holes in the substrate, they are pushed away from the channel. They are pushed away from the channel. When they are pushed away from the channel and electrons are collected near the channel, these are all electrons, then you can apply a VDD or VDS, and current will flow from this side to this side, and it will complete the circuit. Drain current can flow. Okay. And in this entire operation, one thing is very interesting to note. One thing is very interesting to note down, that once we apply VGS to the gate, gate current is zero. Gate current is 0 amperes. Why? Because there is an silicon dioxide. This is SiO2. Okay. This is insulator layer. SiO2 insulator layer है. क्योंकि gate is completely insulated from the substrate or from the channel or from the body or from rest of the device, so current cannot flow, charge cannot flow through the insulator. So gate current is nearly zero. Gate current is nearly zero. Gate current is nearly zero. तो अगर आपने देखा होगा, हमने BJTs में input characteristics पढ़ी थी. Input characteristics हमने कहा it is a plot between input voltage, input current versus input voltage, V input. Okay, so I input versus V input. वहाँ पे हुआ करता था IB input current and maybe VBE input voltage. क्योंकि यहाँ input current हमेशा 0 होती है, तो यहाँ input characteristics नहीं होती है. यहाँ जो ग्राफ बनता है, यहाँ बनता है ट्रांसफर characteristics का. उसमें हमेशा ID is the output current. Okay, तो input voltage होती है VGS versus output current ID. So it is always like this, VGS versus ID. तो इसमें input characteristics नहीं होती है, because IG is eventually 0 because there is an insulator there. Now see, these are different VI characteristics or transfer characteristics of devices. Depletion में मैंने कहा, depletion based MOSFET or depletion type MOSFET में channel is initially present. Channel is present. तो ये डिवाइस इनिशियली ऑन होती है, इसमें आपको इन्वर्शन वगैरह नहीं करना पड़ता है. चैनल इसको फैब्रिकेट ही ऐसा किया जाता है दैट चैनल इज ऑलरेडी प्रेजेंट. तो व्हेन there is VGS is 0, when there is no gate voltage applied, VGS is this line. Okay, this line is VGS. अब ये 0 है. 0 means this point. When VGS is 0, channel is already present, तो कुछ drain current flow होगी. वो drain current होती है because of VDD से. And when you apply VDD, that is a voltage between drain and source, when you apply some voltage, current can flow. तो initially आपको इनपुट गेट कंट्रोल, जो गेट कंट्रोलिंग टर्मिनल है, गेट में आप वोल्टेज दें या ना दें, ये तो इनिशियली डिप्लीशन टाइप मॉसफेट ऑन होते हैं. लेकिन जब आप इसको, अगर आप इसको ऑफ करना चाहते हैं इस डिवाइस को, तो आपको एक नेगेटिव VGS देनी है ताकि इसकी करंट डिक्रीज हो जाए, डाई डाउन हो जाए टू 0. सो द पॉइंट where it turns off is known as VP. It is pinch off point. Pinch off point, जैसे वो JFETs में मैंने अभी दिखाया था, pinch off में बेसिकली रिवर्स बायस से हम चैनल ही ब्लॉक करते हैं. तो यहाँ पे भी वैसा ही कुछ होता है. In pinch off point, you know the channel disappears in depletion type MOSFET, then it turns off. Okay, then it turns off. So you can see that the depletion type MOSFET is initially on, and you are required to apply certain gate voltage to turn it off. ऐसी devices normally हमारे electronics में पसंद हम नहीं करते हैं, because you know if we do not apply certain input, they will be still conducting. क्योंकि बैटरीज तो हमारे सिस्टम्स में होती हैं, हमारे मोबाइल फोन में ऑलरेडी बैटरी कनेक्टेड होती है. तो ऐसी डिवाइस अगर डिप्लीशन टाइप मॉसफेट हम लगाएंगे, ये नॉर्मली ऑन होती हैं, तो दे विल बी टर्न्ड ऑन इवन इफ वी आर नॉट अप्लाइंग इनपुट वोल्टेजेस, दे विल बी डिसिपेटिंग योर बैटरी. सो वी अवॉइड जनरली डिप्लीशन टाइप मॉसफेट. एनहांसमेंट में द चैनल इज इनिशियली एब्सेंट. चैनल इज इनिशियली एब्सेंट. So channel needs to be created. Channel needs to be created. There is no channel between source and drain terminal. The channel needs to be created. तो इसमें channel पहले बनानी पड़ती है. तो इनिशियली ये ऐसे होगा, इसमें कोई चैनल नहीं है. आप पॉजिटिव वोल्टेज गेट पे अप्लाई करें, वही होगा. एक्यूमुलेशन होगा, देन वीक इन्वर्शन होगा, देन यानी डिप्लीशन होगा, फिर उसमें इन्वर्शन मोड आएगा. उसके बाद इन्वर्शन में आप कहेंगे चैनल बन गई एंड then the device can connect, it can work. So इसकी अगर ट्रांसफर कैरेक्टरिस्टिक्स देखी जाए वो ऐसी हैं. When VGS is 0, there is no drain current. Drain current is also 0, so device is not conducting. When you increase VGS and you cross VT is this point, the device will turn on and it will start conducting. अब जितनी VGS और increase होती जाएगी उतनी device और on होती जाएगी, उतनी आप इसको इसमें current जो है that will increase. Okay, that will increase. So I'll take attendance and then we'll continue. Six, 7, and 8. Okay. So this is transfer characteristics. Transfer characteristics of MOSFET. Okay, this is transfer characteristics of MOSFET. Now see, if VGS is varied, अगर VGS को vary किया जाएगा, ठीक है? If VGS is varied, that is input voltage is varied in the MOSFET, then different drain currents can be obtained or different curves can be obtained. तो वो यहाँ पे आपको दिखाई गई हैं. These are the various curves. इसमें मैंने शायद I have uploaded a lecture. I have explained there that there are different modes. One is known as, this is known as saturated mode. तो यहाँ आपको device constant current देती है. This is saturation area. और जो ये region है इसको कहते हैं triode region. तो यहाँ जो आपकी MOSFET है, the curve is somewhere linear also. So in this region, in triode region, MOSFET acts as a resistor, because अगर आप resistor की VI characteristics देखेंगे, it is Ohm's law linear है. तो यहाँ पे भी कहीं linear ही है एक region, तो it acts as a resistor, लेकिन वहाँ पे वो saturated region है. तो मैंने शायद दूसरा lecture इसका upload किया है, आप उस पे देखिए. I'll stop this topic here. We'll start another one. किसी को कोई सवाल पूछना है about MOSFETs, you can ask me. Otherwise, I'll stop now.
काम करते हैं
इसमें MOSFET चाहे आप सैचुरेशन रीजन में काम कराएं या इसको ट्रायोड रीजन में, इसकी एप्लीकेशन ट्रायोड रीजन में भी है, इसको सैचुरेशन रीजन में भी है. यू हैव अ कोर्स ऑफ VLSI डिज़ाइन, उसमें MOSFETs को बहुत अच्छे तरीके से पढ़ाया जाएगा.